Thank you for the introduction and for the opportunity to tell you a couple of things about unipotent group action here. The title is like a teaser because I'm not very sure to come to this kind of application. So my plan is rather to give you some kind of overview of what can be done concerning unipotent group structures on, say, projective varieties. So try to define what I mean by this, and the topic of the talk will be where to find these, how to construct these, what can be said about these. I will mention a couple of names. Montero, Liendo, Kishimoto, Fujita, I could add 3 or 5 more. The thing is, most of what I will tell about was discussed in kind of informal seminar this fall in Poitiers, where all these people were. I had the intention to clean the output of this discussion, but I didn't find the time. So it's a kind of report on a not really joint work, not really in progress, right? It's overview of what was discussed. So what is a U structure? So U will be, and just for safety, walk over a field K, and the characteristic is 0. So U will be a unipotent K group. So basically something which you can embed into the group of linear automorphism of a K vector space as a unipotent, the lower triangular matrices. So, okay, basic example would be n copies of the additive group, or well, any subgroup like that in some GLM. So definitions. A U structure on a scheme, K variety if you wish, is an action, is an effective action. Let's call this guy X. With a risky dense an orbit. If you are familiar with steric variety, it reminds you some definition, right? So maybe a trivial example, U acting on itself by translations. So you think about this definition, a unipotent group has an underlying variety which is just an affine space. So we are speaking in that case about some unipotent group acting on an affine space, right? Okay. So and basic fact is let's give a name to this open orbit Ux. Basic fact is that Ux is always U equivariantly isomorphic to U acting on itself by translation. So once again, it looks like very much toric variety. So assume there is a point in your open orbit, then the open orbit is exactly the orbit of the point. And you know that after a finite étal base change, you just base change, there is a point in that orbit. So this tells you this orbit is a torsor under your unipotent group, and this torsor is trivial. Effective. So if the stabilizer of a point in the open orbit will be, it cannot be non-trivial, because otherwise it would act trivially on a Zariski-dense subset. No. No. Yeah. You can have J square action on something so that every point has stability. So GA, I agree. I agree. I mean that the corresponding map to the automorphism group functor is a monomorphism. Yeah. Maybe this will become clearer in the example. What I mean. So basically, this open orbit is just like the group acting on itself by translation. Or, OK, I'll temporarily solve this issue by saying that the orbit has the same dimension as the group, if you wish. OK? In any case, then there won't be any issue, right? if we assume this. OK, so the second fact is if you assume X is quasi-affine, if X is quasi-affine, then, well, X is Ux. This comes from the fact that, unlike orbits of tori, orbits of unipotent group on quasi-affine variety schemes are closed. So your open orbit is open and closed. So it's everything if you assume X is connected. Right. So this tells you there is no interesting local affine model, unlike toric varieties, for instance. And third fact is, in general, a point X in X does not have any U-stable affine upon neighborhood. So if you were working with toric varieties and the split tori, the theorem of Sumiro would tell you that every point has an open T-stable neighborhood. And so your problem would be to describe how you glue local models along intersection. So here I'm telling you there is no interesting affine model, and you cannot reduce the study of these things to gluings. Right? Yes. That's another story. It will come later. Yeah. Well, no, but here it's just the group acting on itself by translation. Right. Any kind of GN action on AN is the standard one by translation, up to isomorphism, up to conjugacy. But if in a global case, so that's my final comment about this fact, this is more global question. If you want to describe a U structure on varieties, it's not a problem of describing local models and how you glue this. And so in particular, it's something which is good to study on projective varieties. So maybe I should illustrate this. So you just let GA act on P1. Just by translation, say. So your open orbit is like x1 non-zero, x0 non-zero, sorry, which is just A1, and on which the group act by translation. And well, if you take the point 1, 0, it has no invariant affine open neighborhood. Whenever you pick a point in the neighborhood of that, its orbit is the complement of the point, right? Okay, so that's the picture, and now let me tell you why. You could be interested into U structures. Well, it looks like toric variety in some sense, and you might expect there is some kind of combinatorics behind this thing, so trying to understand how it works is of interest. The abelian case is a particular case, but there are many other non-abelian unipotent groups, and understanding what is the difference between an action of abelian unipotent group or non-abelian on a variety, what kind of effect on the geometry of the variety it has, might be of interest. Another point is that variety with a U structure is an equivariant partial completion of an affine space. Right. It contains an open orbit whose underlying variety is just an affine space. So if you look at, say, projective varieties with U structure, they appear a natural compactification of affine spaces. And this has been a long-standing problem to try to figure out what can be said about compactification, projective compactification of affine spaces, for instance. It also tells you that if you're interested in more arithmetic viewpoints, you have variety which contain big affine open subsets. So they are full of rational points. You might be interested into counting these rational points. So then you will have to see what happens on the complement of the open orbit, that kind of stuff. And from the viewpoint of birational geometry, I'll come back to this later. If you look at projective compactification of this, take some equivariant resolution of singularity, you end up with a smooth projective variety with an action of a unipotent group, which contains a big copy of AN. So this variety has non-pseudo-effective canonical divisor. You're in a position for running MMP on that. It will be out of the setup. U equivariant will preserve the open orbit, and you will terminate with Fano variety, with mild singularity, or maybe a Mori fiber space over a base. And so ultimately, you might be interested to understand who are the Fano varieties with a U structure, who are the Mori fiber, strict Mori fiber spaces with U structure. Try to imagine how the U structure fit with the fibration. Basically, there should be some U structure on the base and U structure on fibers, but they have to be related in a certain way. And if you're only interested in compactification of affine spaces, working instead with equivariant compactification of unipotent group gives you a much more rigid geometry. The problem with MMP when you try to construct compactification of AN is that you run some MMP and you have no control on what will happen to your AN. I mean, it tells you there are contractions, there are flips, flops, etc. But here, everything will be equivariant, and your open subset is precise, your open orbit is precisely an affine space. So whatever will happen in this MMP, it will be equivariant, so in the end, you get a compactification of AN of a very special type, because it's an equivariant one instance. Okay? And completions of affine spaces. So it's a simplified approach to constructing some compactification of AN if this is your purpose. Okay, so now how do you construct such structure? Right? How? Because, well, you have to give yourself an action of a unipotent group so that you have an open orbit, right? So let's say X is affine. So what you want to do is to give a representation of your unipotent group into the automorphism group functor of X, and guarantee that the corresponding action gives you as an open orbit, right? So first thing you can try to do is differentiate. So now this goes from the Lie algebra of your unipotent group, which is just a nilpotent Lie algebra of high dimension. You differentiate this, so I'll cheat a bit. Lie algebra of this group, I will identify it with the set, the Lie algebra of derivation from A into itself, like vector fields, global vector fields. And you get this, and basically the image, so this is a representation. Well, this is a morphism of Lie algebra. Here, this is just a bracket of vector field. And with image, and that's the crucial thing, with image, contain a subset with some nilpotency property. Right. This guy is a nilpotent algebra, and I'm saying that in some sense the image of elements here have to be nilpotent vector field in the appropriate sense. So if you started with just a representation into linear transformation of a K-vector space, really you go to this Lie algebra, and the image is precisely consisting of nilpotent endomorphism image. Nilpotent endomorphism. So the analog here, in that case, the image consists of what of so-called locally nilpotent derivations. Or vector fields, if you prefer this language. So what does it mean? I give myself a derivation, and I say it's locally nilpotent, is locally nilpotent if whenever I take an element of A, it belongs to the kernel of the iterates of D for a certain iterate, which depends. So it's not a nilpotent endomorphism, it's like a pointwise nilpotent. Its index of nilpotency depends on the element. Such that okay. So typical example would be, say, you have GA acting on your X, call it mu. You look at the corresponding morphism of rings of global sections. And when you differentiate, what you are doing is basically considering this derivation. So here, it sends A to some polynomial, right? Maybe AI, CI, and you are just looking at the first coefficient. And conversely, whenever you start with such a locally nilpotent derivation, you can go the other way and take formally the exponential. A priori, you will land into the ring of formal power series. But with that condition, on every element, dm becomes 0 after some step, so the image of every element is actually a polynomial of degree, which can be arbitrarily large, but a polynomial with factors. So in some sense, this locally nilpotent derivation, they just correspond to vector fields which are algebraically integrable. They correspond to algebraic one-parameter flows on your variety. Okay, so basically, that's the correspondence in the affine case. An action of u on x fine is the same as a morphism of the algebra as my zero in some sense, whose image consists of locally nilpotent derivation. And of course, since this is a morphism of Lie algebra, if you take two elements here, the associated locally nilpotent derivation, when you compute their bracket as vector field, this has to be the image of the Lie bracket on the source, right? Sorry. Where this Lie bracket is the Lie bracket of vector fields on X, and this is the Lie bracket on the Lie algebra. So, okay, we just saw one direction. If you want to go the other way, you just basically exponentiate this correspondence. The exponentiation of G will give you back your group U. And here, since we have collection of locally nilpotent derivation, we can formally exponentiate, and we get a comorphism like we got before. That's another story. It comes after. So maybe example. If you want to describe an action of GAN on X, this is the same as n commuting LNDs. Okay? If you want to describe an action of, yes. Yeah. Well, no. it's just a GN action. I'm not asking yet there is an open orbit. If you want to describe an action of this group, which is exactly the Heisenberg group of the title, this is the unique non-abelian unipotent group of dimensions 3. Then if you look at its Lie algebra, it's basically generated by 3 vector fields, X, Y, and Z won't be exactly A, B, and C, but and the Lie bracket is basically X, Y is equal to Z, and the rest commute. To 0, except yx, which is minus z. Okay. So to describe an action of this group, you need 3 locally nilpotent derivation, and the bracket of the commutator as derivation of the first 2 has to be the third one. Right? So that's it for describing the action, and now we come to the problem of having an open orbit. Well, this derivation, they are essentially tangent vector field tangent to orbits of your Each time you pick a derivation, this corresponds to an action of GA, and this derivation is like the velocity vector field along the orbit of this action of GA. Now, if you want to have an action with an open orbit, you should at least find a point of x at which your derivation generates the tangent space, right? Because you will cover all possible direction at that point. So basically, this will tell you that the orbit will be open, right? So I just put it as a comment. Then condition for open orbit. There exists x. It's a k-rational point such that the restrictions at x of the derivations in the image of 0 generate the tangent space, the tangent sheaf. This will tell you that starting from this point, using your group, you can basically translate in all possible directions. So at least locally, you will have some dominant map from U to your variety, and you can check that since everything is U equivariant, the orbit of a point like that will be an open orbit. That's the idea. Okay, so good. That was for the affine case, but I told you before the affine case is not interesting. So, but you can basically get the same description for projective varieties. No, we go to the projective case. So now X is like proj, some algebra where A is finitely generated and graded algebra. Okay, but that's exactly the same picture, if you wish. An action of U on X is determined by the algebra homomorphism from the algebra of your group. And now we go to the derivations of A into itself, but homogeneous of degree 0. These are homogeneous vector fields of degree 0. So if you replace this proj by the spec, I'm just describing vector fields on the spec, which are homogeneous of degree 0 for the GM action on the spec associated to the grading. Homogeneous of degree 0 means they commute. Homogeneous of any other degree means they just semi-commute and they do not descend to derivation. Right? So I just have to give myself homogeneous locally nilpotent derivation with respect to this grading. And you have already seen it here, right? In P1. What is the derivation corresponding to this precise action? Well, basically, it's when I differentiate with respect to x1, my degree dropped by 1 with respect to the natural grading, but I put back x0, so I re-increase the degree by 1, I have something homogeneous. So the rest is okay. You want an action of U, so the algebra homomorphism. You want it to have an open orbit. Well, good. At some point of your projective variety, the vector field corresponding to this homogeneous derivation of degree 0 have to generate the tangential. Okay? So maybe let's do another example. Let's say on P2. So I have to cook up, let's say I want a GA² structure. So I have to cook up a pair of commuting locally nilpotent derivation of degree 0. Wow. Not so bad, right? You write, if you exponentiate and see how the action is, so that would be D1, that's D2. It's basically and my open orbit is again x0 non-zero, so that's a copy of A2. On this A2, I'm just acting by usual translation. Okay. Any idea for another one? On the x, no, when x0 is non-zero, this should be strictly equivalent to what I wrote. My claim is that there is another one with different orbits. You see, if you look at the hyperplane, x naught is equal to 0, so complement of the open orbit, the action on it is trivial. Then there is another possible use structure so that the action on the hyperplane at infinity is non-trivial. Let's try to cook it up. I'll probably tell you a wrong formula and we adjust, right? And I keep the same D2. Okay, this remains locally nilpotent. This one is a guy of triangular form. So when I apply it, so it's homogeneous of degree 0, and when I apply it to any polynomial, homogeneous polynomial in x0, x1, x2, I'm dropping the degree in x2 and multiplying it by x1. So after iterating this finitely many times, I kill every monomial in x2, same every monomial in x1, etc., and x0 is in the kernel of that guy. So let's see how it goes. So I'll let you verify that the commutator is 0. It's just exercise. And now we write down the corresponding action. So you have to take exponential of this guy. Right? So basically, I know the game starts. It should be x2 plus d1 x1 plus 1/2 d1 square x0, because I have to iterate twice, and plus x0. That's the second action. And the open orbit is the same. Up to automorphism of this open orbit, it's just J square acting on itself by translation. But no, when you look at what happens when x0 is equal to 0, you just see what? P1 with coordinate x1, x2. But no, the action is basically the standard one, right? It's x2 plus P1, x1, x2. Wait, no, it's x1, 1, x2 plus T1, x1. So my P2, that x0 is equal to 0. So the first action on this line at infinity consists only of fixed points. And here I have just one fixed point, basically 0, 0, 1. And on the rest of the line, I have an induced effective action of G, right? Okay. Oh yeah. Look, here x1 is translated by T1. This x2 is translated by T2, and there is this kind of mixed term in the middle. But if you wish, this one should correspond to the representation of GA given like that. Maybe it's conjugate transpose, but 1/2 of T square. Something like that. These are the two possible linear representation of GA square, which gives you an open orbit. That's basically the idea. Okay, so this tells you that if you want to study variety with U structure, there is something again different compared to toric varieties. Usually, reasonable projective toric variety has a unique toric structure. Here, already P2 has different G square structures. Okay. So, okay. So I have to select what I'll tell you. Okay. Maybe a word about the birational, equivariant birational geometry and what can be done. So back to no equivariant birational. So what do you get in dimension 2? So you start with a normal surface with a U structure, take desingularization. U in that case is J square because there is only one two-dimensional unipotent group, and it's abelian. This is J square. So you run your MMP, and in the end, you find either a Fano variety with a J square of Picard rank 1 with a J square structure. That's P2 with some J square structure, or Mori fiber space over a curve, which is basically a conic bundle over P1, because I started with something containing A2. But since I have a J square action, it's more than a conic bundle, because on the general fiber of this projection, there should be a J action. So the fiber is not a form of P1, it's genuinely P1, right? So in dimension 2, I get exactly two models. P2, which is the Fano case, and at least two J square structures, which are different because they have different orbit profiles, right? And algebra surfaces. Maybe I'm not raw. So, and I have a J square structure on this. So now I take this projection. So I have an induced action of J square on P1. Obviously, there is a kernel, because this action cannot be effective, cannot be a faithful action. So basically what I get is I look at here. So this is a unipotent group, one-dimensional. This is to be GA, and the quotient, call it UB. It's a unipotent group, isomorphic to GA. That one should act with an open orbit on the base because, I mean, the open orbit has to be mapped to something. And whenever I take one point in my open orbit, this guy should act with an open orbit on the fiber, right? So basically, equivariantly, I have UP1 open orbit of UB on P1, and my open orbit UFN is U equivariantly isomorphic to UP1 cross U, let's see, UPN minus 1 X, where PN minus 1 is the fiber over the point of UP1. And this is U equivalent isomorphism. Here I can view U because I have commutative. This is J squared, so it's commutative. I can view my U as just the product. And this guy is acting here, and this guy is acting there. I'm really using the fact that the group is abelian to get this structure, because I'm splitting this kind of exact sequence, UF, U, UB. If I have time, I will tell you what's the problem with, the first problem with the Heisenberg group is that you cannot split. So its structure will be more or less the same, it's more complicated. Okay, that's for dimension 2, except that we have to decide on P2 who are the conjugacy classes of P square structure, and the same here. On Hilbert surfaces, there can be many, right? I won't spend much time on this. I prefer to tell you a bit about dimension 3 and what happens with this Heisenberg group. So, dimension 3. So, you start with your smooth projective variety with a U structure, apply MMP, and let's say for simplicity that the output of your MMP is a smooth variety. So, your possibilities are smooth Fano threefolds. With, wow, no, there are two unipotent groups to consider. Either A cube or this Heisenberg group H, which here you can view as a non-trivial extension of G squared by A. That's the guy here. Okay, so you have to discuss for the two. Or you can get del pezzo fibration over P1 with a blah. Or you can get a Mori conic bundle over a rational surface with the same thing. I know it's a case-by-case thing, and what has been partially done so far, it's case of the abelian three-dimensional unipotent group. So for Fanos, okay, so there are two types of results. First, you have to decide which Fano threefold can have a J-cube structure. Obviously, P3. Kind of obviously smooth quadratic. Kind of obviously every smooth Fano variety you can produce from one of these two by blowing up something which is J-cube stable, like a J-cube stable point, a J-cube stable line, a J-cube stable conic, provided that you stay Fano, right? So you go through the list, automorphism groups of Fano threefold, neutral component of automorphism group of Fano threefolds are known. So you go through the list, you check in which case you can find a J-cube, and then you discuss whether you can have an open orbit or not, right? So basically this was done by Pedro Montero and Fu. And in each case, you have the problem of saying, is this structure unique? Right. So for P3, you can imagine it's not unique. It's classified. I will say a word if I have time. For the quadratic, it's known to be unique. This is a result of Elena Charoiko, a student from Ivan Argentsev, if I remember well. This is subtle. And for many others, well, you have the description of the automorphism group. So you are trying to look at conjugacy classes of J-cube inside. The automorphism group are rather small. This is doable. Del pezzo fibration. So here, the fiber, the general fiber are del pezzo surfaces. You should have an induced action of GA on the base with an open orbit, and a typical fiber should be a del pezzo surface having an open orbit of GA square. You don't have much, right? This means it's the general fiber is either P1 cross P1 or P2. Or the smooth del pezzo surfaces, well, I mean, it's in any case, relative Picard rank is 1. But what I'm saying is that on a general fiber, you should have a GA square structure. So the only possibility is like P1 cross P1 and P2. Yeah, like that. So, and you have to exclude the possibility that it's P1 cross P1, but look, instead of looking at the general fiber, you look at the generic one. So the generic one inherits a GA square structure over the function field of P1. But the generic fiber has Picard rank 1. So it's a form of P1 cross P1, having Picard rank 1 on the GA square structure. It's not possible. If you have a GA square structure, basically you must have Picard rank 2. Just unwaving, but that's the idea. These things were fully clarified by Masaru Nagaoka. So, but once again, this does not tell you what are all the possibilities. In the end, you are just speaking about projectivization of a vector bundle of rank 3 on P1. Right? So it's decomposable, but you know there is a GA action on the base, and you want to lift this to a GA cube action on the total space. So there are many choices, right? It's like irritable surfaces. You can have tons of triangular derivation depending on the degrees of your line bundle. That's the idea. Mori conic bundle. And, oh, wait. Yeah, for the moment, this is only for J cube. MCB, unclear. You know it has to be a P1 bundle by the argument I told you before that there should be a GA action on the general fiber with open orbit. There are P1 bundles over surfaces with a GA square structure. Okay, and well, there are a lot to do. I mean, you can already start with P1 bundle over P2 with the two J square structure, which you know. Try to lift this to a J cube structure, for instance. And tell you something about so let's just take a simple example. X is just the projectivization P2. Here we have seen two possible J square structure. So the question is, can you lift any of these two to J cube structure on the projectivization of the tangent bundle? The answer is no. And there are many ways to see this. So you have this J square structure. The tangent sheaf comes with a canonical J square linearization. And what you want to cook up is a vertical J action, which complements, well, saying that it has a canonical J square linearization tells you there is a unique way to lift this J square action to something here, right? And now you want to cook up a third J action, which should commute with the other one and act vertically. So the third J action, which would complement the lift of these two so that you have an open orbit, should come from a morphism from GA to out X TP2, out P2 TP2, commuting with the J square action plus commuting. This guy has no non-trivial interest, no one-dimensional algebraic group of relative automorphism. That's a stable vector bundle. So just this guy cannot exist. There is no J cube structure on TP2 just for this reason. But there is an Heisenberg structure. But essentially because TP2 is GL3 oriented by upper Borel subgroup, right? So it has a natural action of the Heisenberg group. What's wrong here, right? What is the difference? What happened? What happened is exactly the failure of that when the group is not unipotent, is not abelian. Here I said to get a J cube structure here, I have my induced J square structure here. I just need to find a commuting vertical J action. But I implicitly use that thing, that my J square action on the base naturally lift to a J square action on the top of on the bundle itself. Right? But if the group is not abelian, it might just happen. I cannot lift this J square action. Right? The guy is an extension here. I'm starting with the image of H acting as J square. But there is no splitting here. So I can basically not lift this J square action. If I try to lift this J square action, what I will produce is basically on the total space of P of TP2, two non-commuting derivations of degree 0, which are locally nilpotent, and whose commutator is, well, a third locally nilpotent derivation, giving me the guy in the kernel. So this just illustrates you the type of problem you have to figure out when you want to study U structure on bundles. For Fano variety, dimension 3, if you want to do the Heisenberg group, well, you do the same as Montero and Fu. You go through the list of automorphism group, you check which automorphism group contain a copy of the Heisenberg group, you check whether there can be an open orbit, and that's it. But for del piezo fibration, this is basically the same thing. But for P1 bundles over surfaces, that's another story. I conclude maybe with just the last example. So take any of these two G-square structure on P2. They both have a fixed point 0, 0, 1, right? Any of the two. And you take this is fixed point, a G-square fixed point. Now there is a natural bundle you can hook up out of this. You take basically there exists a unique canonical extension such that this guy is locally free of rank 2. So you can look at this P of F, or P2, wherever it is. It's not a direct sum of line bundle. So this guy was G-square stable. This guy has a G-square linearization. So this guy should come with a lift of the G-square action on P2. And now, depending on the G-square structure you started with, you have different possible lifts. If you start with the toric G-square structure, toric means that's the first one I wrote. That's the one which is naturally normalized by the action of the toric structure on P2. Then get a J cube structure. Of F. So you just have to verify. You take the natural possible lift of the generator of this J square action. You check that they commute, and you manage to cook up a third derivation. If you start with the other one, it does not lift to a J cube action. If you start the other one, the only possible lift, only way to lift, is to an H structure. There's no way to cook up a GA cube structure on P of F such that when you project back to P2, you get the second type of GA square structure. So actually, this is through this example which we came to the problem. We had this natural sequence, the two structure. We wanted to say, okay, how can we lift to P of F? And after writing tons of derivations, saying, no, but they are not commuting. There is a problem. This should not be correct. Just notice that their commutator was a third locally unipotent derivation of degree 0, and that everything was generating a group isomorphic to the Heisenberg group. So even when you start with nice abelian thing in dimension 2, you will have this kind of lifting problem. And the higher you go in dimension, the more complex the unipotent group become. In dimension 4, this is still tractable, like GA cube, Heisenberg cross GA, an extension of Heisenberg by GA, and that's it. And starting from dimension 7, if I'm not incorrect, there is a moduli. So since birational geometry tells you that you reduce to fibration, etc., it looked good, but in the end, you have all these extension problems to consider. So that's why it's a work not really in progress, basically. Dimension 3 should be fully doable, starting from higher dimension, maybe some specific cases. Thank you. question. I didn't try, but I would say certainly yes. But you see, basically on TP2, you can leave both GA square action, both GA square structure to some unipotent group structure on PTP2, which has to be the Heisenberg structure. So far we didn't see any example of a GA square structure on a surface which you cannot leave to the total space of an equivariant, of a GA square equivariant bundle, in such a way that you can complete. Well, if you wish, but there are more interesting unipotent group in positive characteristics. Yeah, well, I mean, hidden everywhere is this correspondence between unipotent group and nilpotently algebra. This is characteristic 0 business. Yeah, well, yeah. I mean, it's out of convenience because writing derivation instead of a full system of iterated derivation. Yeah. Well, I mean, every statement which is characteristic independent is okay, right? This is if you want to go this direction. For GAN, this does not make big difference. For Heisenberg, it doesn't as well. It's just for